All right, we're going to look at some problems that will help you for your upcoming test 3 on some of our applications of derivatives. So if we look at our first problem, this says find the linear approximation to the function f of x equals x squared tan pi x at x equal 1/4. So this is where we're trying to approximate our function with a linear equation. So if you recall, we had a tangent line approximation. We said the tangent line approximation was f prime of c, x minus c plus f of c. So in this case, our c value is going to be this 1/4. So really all I have to do is find what f prime of c is and what f of c is. Now f of c I can do right away is just doing what is f of 1/4. Well, that's going to be 1/4 squared plus tangent of pi times 1/4, which is pi over 4. So obviously I need my unit circle to kind of know what that value is. Pi over 4 is a pretty easy one. Square root of 2 over 2, square root of 2 over 2. And for the tangent, recall tangent on the unit circle is y over x. So if I divide radical 2 over 2 by radical 2 over 2, I should get 1. So f of 1/4 will be 1/16, 1/4 times 1/4 plus 1. And so that's going to give me 17/16. So that is this f of c part I have here. Now to find the f prime of c, I obviously need f prime. So let's find the derivative. So f prime of x is 2x. The derivative of tan x is secant x, but we have this inside of pi x. So the derivative of pi x is just pi. It'll be pi secant squared of pi x. So using the chain rule, our inside is pi x, derivative is pi. Derivative of tan is secant squared of that pi x. So if I want f prime of 1/4, we'll do 2 times 1/4 plus pi times secant squared of pi over 4. Now the secant of pi over 4 is going to just be the flip of the x-coordinate. So secant of pi over 4 is just square root of 2. So f prime of 1/4 is just 1/2 plus pi times the square root of 2 squared. And again, secant pi over 4, just the reciprocal, 2 over radical 2. You can rationalize the radical 2. So f prime of 1/4 is 1/2 plus 2 pi, because radical 2 squared is just 2. So now that I have f of 1/4 and f prime of 1/4, it's really just plugging into this formula. So my tangent line is f prime of c, which is this 1/2 plus 2 pi, times x minus 1/4, plus f of c, which is 17/16. So this would be the line that would be tangent to this equation at 1/4. So if I were to graph this function here, and this tangent line function here, we would see the line here touches the graph at one place, barely touches that curve at x equal 1/4. Number 2 says find the differential of y equals e to the x. So the differential is just a way to approximate the change in y with the change in x. So if you recall, the differential dy is just simply equal to f prime of x times dx. So if we consider our function e to the x, then our differential is just going to be f prime, so the derivative of e to the x is e to the x times dx. So this is how much the y value would change at a given x value with a given change from that x value. Now this is fine, but what we'll use this more for, and what we've used it for in the past, is to approximate some different values using these differentials. So for example, we did quite a few of these problems where we said, let's use the differentials to approximate the square root of 99. To do so, we use the function square root of x. Now, we know that f prime of x is going to be 1 over 2 square root of x. Now again, reason why, obviously this is x to the half I could bring the half down, take one less power, all that good stuff. So I'm trying to approximate the square root of 99. Well, if x equals 100, then the square root of 100 is really nice. It's 10. So really all I have to do is figure out how much does the y value change from when x is 100 to when x is 99. So to do that, to approximate the square root of 99, I'm just going to take 10, which is the square root of 100, and I'm going to add some change in y. Now obviously that change will be negative because it has to be smaller than 100. So in this case our x is 100 and our dx is going to be negative 1. So since our differential dy is going to equal 1 over 2 radical x dx, to find this magical change in y, we'll just plug in. So this is 1 over 2 times square root of 100 times negative 1, because dx is negative 1. So dy is going to equal negative 1/20. So now that we have that change in y, we'll just say that the square root of 99 is going to be 10 minus 1/20. So square root of 99 will be approximately 199 over 20. So if you check square root of 99 and you check 199 over 20th, in any old calculator, it should give you very close to the same value. Okay, number 4 says, for the following example, determine whether the mean value theorem can be applied on the function in the closed interval a to b. If the mean value theorem can be applied, find all numbers in the open interval such that f prime of c equals f of b minus f of a over b minus a. So if you recall, the things we always said about this is f had to be continuous, which sine x is just a nice sine periodic wave plus x is fine. And f prime must exist. It has to have a derivative on the interval. Well, f prime is pretty easy in this case. F prime is just 1 plus cosine x. So we want to know, since this does have a continuous function that has a derivative, there is some value for which f prime of c equals f of b minus f of a over b minus a. So our interval a is 0 and b is 2 pi. So the first thing I do is figure out what is f of a and what is f of b. Now it doesn't say prime, so we're literally plugging into the regular function. So that's going to be 0 plus sine of 0, which is going to be 0. And then it's going to be 2 pi plus sine of 2 pi. Sine of 2 pi is again 0, so this is 2 pi. So when I form my difference quotient, f of b minus f of a over b minus a, so f of b is 2 pi minus 0 over b minus a. Now b minus a is just the values in the interval, so 2 pi minus 0 again. So this gives me 1. So the idea is this difference quotient is equal to the derivative at some point in this interval, assuming the mean value theorem is true. So I'm going to say the derivative is equal to this one we found at some point. Subtracting 1 just gives me cosine x equals 0, and cosine x equals 0 at pi over 2 and 3 pi over 2. It's where the x value is 0 on the unit circle. Both of those are on my in my interval, because it's 0 to 2 pi, so both of them are valid solutions. I don't have to look for more. I don't have to add 2 pi or subtract 2 pi to find more, because my interval is only between 0 and 2 pi. But if I change it to 0 to 4 pi, sure, I could add it as many times as I want. Now our second problem here says, same idea, do we have the mean value theorem, does it apply, where is it at? So our interval is from 2 to 7, but this one is actually a really quick problem, because if you notice here, x can't be 6, because 6 is going to cause a vertical asymptote to occur. So we know f is not continuous on the interval 2 to 7. So right away, because that discontinuity is there, we can disclude the theorem being applied there. Still could happen, but in general, that is not going to be allowed. So our next problems talk about increasing, decreasing, concavity, points of inflection, max and min. All these really deal with first and second derivative. Remember, the first derivative is always talking about increasing and decreasing because it's how the function values are changing. And the concavity is how the increasing and decreasing is changing, so it's going to be f double prime. So for both these, we make sign charts. We talk about max and min and inflection points. So I'll go ahead and do that. I'll go ahead and first find the first derivative. So the first derivative is 12x cubed minus 24x squared minus 36x. So obviously I want to see if there are any critical values where this is 0 or undefined. It's not undefined anywhere, but if I set it equal to 0, we could certainly work that out. The easiest thing I see to factor this is I can pull out a 12x. Pull out a 12x, get x squared minus 2x minus 3. And then that is going to factor as x minus 3, x plus 1. So these are my three factors. So 12 times, so my three critical values are 0 because 12 times 0 is 0. 3 because 3 minus 3 is 0. And then negative 1 because negative 1 plus 1 is 0. So my goal is to do a sign chart on all of these values, to do a sign chart with all these values. So I'll go ahead and do the first derivative sign chart over here, and then I'll do the second derivative sign chart. So negative 1, 0, 3. We'll call this region A, B, and C, and D. So now for each of these regions, we'll go ahead and pick a number. So maybe I'll pick negative 2, and I'll pick negative half. I'll pick 1, and I'll pick 10. So the idea for a first derivative chart is we're going to plug these numbers into the first derivative and see if they're negative or positive. So I'm just going to put it in here into these factors. So negative 2 makes it negative. Negative 2 minus 3 is negative. Negative 2 plus 1 is negative. So it's essentially 3 negatives, so this region is negative. So that means the function is decreasing. Negative half times 12 is negative. Negative half minus 3 is negative. Negative half plus 1 is positive, so that region is positive. So it's increasing. You can just plug them into the original derivative. I'm just kind of doing it with factors because I don't want to use a calculator. 12 times 1 is positive. 1 minus 3 is negative. 1 plus 1 is positive. So two positives and a negative is a negative, so now it's decreasing. And then 10 is going to make everything positive, so it's positive, so it's increasing. So we can say this is increasing from negative 1 to 0 and 3 to infinity. It is decreasing from negative infinity to negative 1 and 0 to 3. So this also tells us where the mins and maxes are, because obviously if it's going from down to up, this is going to occur at a min. If it's going from up to down, it's a max, and same thing over here, it's a min. So if I want to finish this up and find the maxes and mins, the mins are going to be at negative 1, and they're going to be at 3, and the max is going to be at 0. Now obviously I'd have to plug these into the function because the y value is at the function. This one's 0 because it makes all the x's 0. Negative 1 is going to make it negative 3. No, I'm sorry, it would be 3. Then it would be plus 8, which is 11. And 11 minus 18 is negative 7, I believe. I'm just plugging it in to the original function here. So plugging 3 is going to give me negative 135, so that one's way down there. So those are my two mins. We've got a max, and we have the increasing, decreasing intervals. So essentially concavity will be the same idea, except for I'm going to use the second derivative instead of the first. So let's just keep going from here. So my second derivative, f double prime of x, is going to be 36x squared minus 48x minus 36. So when I set that equal to 0, I can take out a 12 for sure, and I'll have 3x squared minus 4x minus 3. Now the 12 is kind of pointless at this point because it's just a 12. So I could just use, like, say, quadratic formula for this one to find the zeros. So if I want to use quadratic formula here, there's more room on your paper than mine. Negative b plus or minus square root b squared will be 16 minus 4 times a times c all over 2a. I'm ignoring the 12. I'm just doing the thing inside because the 12 is just a number. It doesn't really affect it. So this is 4 plus or minus the square root of 16 plus 36, which is 52 over 6. So those are going to be the values, and I could simplify this. I know that square root of 52 simplifies, but for our purposes, this is okay. So on our sign chart over here, I'm going to make sure that on my sign chart, I have 4 minus radical 52 over 6, and I have 4 plus radical 52 over 6. So it would be somewhat helpful to know what those values are, because otherwise I'm going to have a tough time picking what test points are. So if I just put these in the calculator, this one is about negative 0.5 something. And then if I do this one, it's about 1.8. That'll just help me get my test points. So I'll pick 0, and I'll pick negative 1, and I'll pick 2. So in the second derivative, 0 is definitely going to give me a negative, because 3 times 0 squared minus 4 times 0 minus 3 is negative. If I put in 2, I'm going to get 12 minus 8 minus 3, which is positive. And then if I put in negative 1, I'm going to get 3 plus 4 minus 3, which is positive. Just plugging them into the second derivative here. So concave's up, concave's down, concave's up. So concave's down on 4 minus radical 52 over 6 to 4 plus radical 52 over 6. Concave's up, negative infinity to 4 minus radical 52 over 6. And 4 plus radical 52 over 6 to infinity. So there are inflection points at both. So this is an inflection point, and this is an inflection point. Because remember, anytime it changes from concave up to concave down, it's an inflection point. Now the awful part is you'd have to actually plug these in to get the y values, but obviously I would make them much nicer on your exam. Hopefully. Let's look at another one of these kind of examples. We'll do one that has a square root in it. A little more complicated. So if we look at this, we'll do the first derivative. So the first derivative is going to be f prime of x is 1 minus 1 over 2 square root of x. We've done this several times. So if we're setting it equal to 0, we get 1 minus 2 radical x. So I want to get the x by itself. I'm going to go ahead and add the 2 radical x to the other side. And then what I can do is I can flip this and just get 2 radical x equals 1. Because you can always flip both sides of an equation, no problem. So I'll divide by 2, square root of x equals 1/2. So squaring both sides give me a critical number of 1/4. So not a terrible number, because the good news is if you have 1/4, then you only have one critical number. You can have 0 and 1 as your two intervals. There's only two intervals because there's only one critical number. So if I put in 0 to the derivative, I have an undefined value, which is a problem. So we have to remember what kind of throws us off here, remember, it's a square root in the original, which is only good from 0 to infinity. So we're going to have to start our thing at 0. So we can't go left of 0. There's no graph left of 0. Okay? So I got to pick a different critical value, something between 0 and 1/4. How about 1/8? And then something bigger, say 1, for our two regions. So if I put 1 in there in the derivative, it's 1 minus 1 over 2 square root of 1, so it's 1 minus half, which is positive. I'm just putting this into the derivative. You are welcome to just plug it in with a calculator that does the same exact thing. So if I plug in 1/8, I'm going to get 1/8 minus the square root of 1/8. Now the square root of 1/8 is going to be bigger than 1/8, so it's going to be negative. So we're going to be decreasing and then increasing. So we're decreasing from 0 to 1/4, and we're increasing from 1/4 to infinity. So that's going to mean there is a min, no max, because it's going down then up. So the min is at 1/4. And I'll plug this one in. So we get 1/4. So f of 1/4 is 1/4 minus the square root of 1/4, which is 1/4 minus 1/2, which is negative 1/4. So that's my increasing and that's my decreasing, and it has a min in this case. Just because these problems are kind of repetitive, I think I'll just do the increasing, decreasing on this one, and then our last problem on this, we'll do concavity. That way we've kind of got some practice on all of them. But they all work basically the same. Set up your sign chart, pick some values, and see if it's negative or positive. So this is the one we can do just the concavity test on. We'll just check and see if it concaves up or down. Now the idea is you have to find two derivatives, so 1 plus cosine x. The second derivative is just negative sine x. So when I figure out where that's 0, now obviously I have to be somewhat careful because there's no interval here. Let's just say we're going 0 to 4 pi. So I'm trying to figure out where sine is 0. Well, I know it's 0 at 0, which is an end, and 2 pi, which is an end, or is in the middle, and 4 pi. Sine is 0 at all those, and as well as pi and 3 pi, because that would be over on the left side of the unit circle where y is still 0. So if I think of my second derivative sign chart, it's going to start at 0 and end at 2 pi, or 4 pi, because that's just the interval I talked about. So I'm not going to have to put 0, but I'll put pi, and I'll put 2 pi, and I'll put 3 pi. So we got regions A, B, C, D, and that's it. So we have to kind of pick some points in each of these. So I'll pick pi over 2, 3 pi over 2, how about 5 pi over 2, and 7 pi over 2. You can pick whatever you want. So I'm basically going to plug these into the second derivative, which is negative sine x. Now, sine x at pi over 2 is 1, so this would be negative 1 in the second derivative, so that's negative. So concave down. Sine of 3 pi over 2 is negative 1, but negative 1, because remember, it's negative sine, is positive, so concaves up. And 5 pi over 2 is the same sine value as the first one, so it's going to be negative and then the same because it's positive, because we're just talking coterminal angles. So we have concaves down on 0 to pi, and then also on 2 pi to 3 pi. Concaves up on the other two intervals, which would be pi to 2 pi and 3 pi to 4 pi. Now, anywhere the inflection changes, you're going to have an inflection point. So we have lots of inflection points in this case. So we'll have an inflection point at pi, we'll have an inflection point at 2 pi, and we'll have an inflection point at 3 pi. Now the problem is I have to figure out what they are plugged into the original equation. So the first one I'm putting in pi, so pi plus sine of pi. Sine of pi is 0, so this would be pi. You'll see a pattern here. 2 pi plus sine of 2 pi, but sine of 2 pi is 0, so this is 2 pi. Just plugging into this original. Sine of 3 pi is also 0, so 3 pi plus 0 is 3 pi. So those are my 3 inflection points. This is where it turns from concave up, concave down. Can't use this, obviously. You can't use a graphing calculator on a test, but I think it's a great idea to check your work when you're looking for these, just to verify that what I'm telling you really is true. All right, now we're going to look at some of our word problems. We have the old related rates, which was from section 1. We'll talk about some optimization problems as we finish this up. So this is a car is being compacted into a rectangular solid. The volume is decreasing at a rate of 2 cubic meters per second. The length and width of the compactor are square, but the height is not the same length as the width and the length. The length and the width of the walls are moving toward each other at a rate of 0.25 meters per second. Find the rate at which the height is changing when the wall lengths and width are 2 meters and the height is 1.5. So this problem sounds really complicated, but it actually gives us a really easy out. And the really easy out in this case is that we are doing a rectangular solid where this bottom base is square. So what I know is this width and this length are the same, so I can literally just call them both W or X or L or whatever you want. Now this height is going to be different as this car gets compacted into this compactor. So that's going to change, okay? Now, what it's telling us is a couple things. As it says, the volume is decreasing, so that's a rate. So the volume is decreasing, dV dt, at a rate of 2 meters cubed per second. So that's going to be a negative. Obviously, it's going down. It says the length and the width are moving toward each other at a rate of 0.25 meters per second. So I'm going to call that dW dt. That's going to be negative 0.25 meters per second because they're getting smaller. It's a compactor, so everything's getting smaller. And we want to know what rate is the height changing when the length and the width are those. So we first have to come up with a formula to start with. This is a pretty easy one. It's volume of a rectangular solid is just length times width times height. So it's just W squared plus H. So length times width times height, W squared times H, will now differentiate with respect to T. So we have dV dt. Now this is going to be a product rule problem because we have F and G. So F prime is going to be 2W dW dt. Remember, anytime you multiply or differentiate with a variable it's not itself, you're going to add that T, times H, which is G, plus G prime, which is 1, dH dt, times W squared. Now we should know numbers for most of this stuff. Let's see. This one is negative 2. The width and the length are 2. And then we have dW dt, which is negative 0.25, and the height is 1.5. Now we want to find dH dt, that's the whole purpose of the problem, times W squared, and the width is 2, so 2 squared is 4. So now I just got to clean this up algebraically. This is negative 2. This is 4 times negative 1/4, which is negative 1. So this is negative 1.5 plus dH dt times 4. So then if I add 1.5, I get negative 0.5. I'm just moving this 1.5 over here. Equals dH dt times 4. And then I'm just going to divide both sides by 4. So dH dt is going to be negative 0.125 meters per second. So it's a little slower. The height's getting crushed a little slower than ours, that square bottom, because it was negative 0.25 meters per second. But in general, it makes sense. It's getting smaller. It's getting compacted into this small size. So even though two sides are getting smaller, then the height should also be reducing because you want to make sure you're getting a net loss on that volume. So this is the idea with related rates, obviously. Pick what you know, figure out what you're missing, differentiate with respect to t, and it's a lot of substitution of values trying to figure out what we're looking for. Okay, let's look at another one. The edges of a cube are expanding at a rate of 8 centimeters per second. How fast is the surface area changing when the edge is 6.5? So if we think of what a cube is the same on all faces. So if I call these sides S, it's S by S by S. But we're talking about surface area here. So surface area is basically the area of all these faces. And there are 6 faces that all have an identical area, which is just S squared. So if I take the derivative of this with respect to t, I'll get dSA over dt, so the derivative of the surface area with respect to time, equals 12s ds dt. So then I know that my surface area is changing when the edge, I simply just plug in. 12 times 6.5, and the area at each edge is expanding by 8. So I have 12 times 6.5 times 8, so I'll just figure out what that is. And that's going to give me 624. And our unit's going to be square centimeters per second. Because it's area, so it's got to be squared units. Now, these are pretty straightforward related rates problems. I would encourage you to make sure you look back at your Pythagorean problems, some of our triangle problems, just all the ones we did, because we want to make sure that we're prepared for any problem that may appear on the test. 6.5. Okay, let's look at some problems doing some maximization. So we talked a lot about closed intervals, and so we have some of the basic problems where we're just finding the maximin of some functions on some intervals. So the big thing is obviously just to take the derivative of these things, and those give you your critical values. And then we'll check those against the endpoints to see which one's biggest, which one's smallest. So the first thing I'm going to do is obviously find the derivative. This guy looks like it's an obvious product rule. So f and g, so f prime g, g prime f. So the derivative of 4x, very simple, is just 4 e to the 3x plus the derivative of e to the 3x. So the derivative of e to the 3x is tricky because remember, it's got a chain rule element. So if my inside is 3x, the derivative of that is 3 times e to the 3x times g, which is 4x. So that could be a little tricky to remember because there is an inside to this exponential function. So f prime of x is going to simplify to 4 e to the 3x plus 12x e to the 3x. So there's our derivative. So we'll obviously want to figure out where that equals 0. So I'll go ahead and set that equal to 0. I could factor out 4 e to the 3x. So if I do that, I have 1 plus 3x left, I believe. Now, the good news is e to any power, anything to a power, can never be 0. So as far as that first factor, we can kind of safely ignore it. But the second factor, 0 equals 1 plus 3x, is certainly okay. Subtract 1, divide by 3, we get x equal negative 1/3. So now for our, and that is in the interval, that's important. So what I check is I want to plug in the regular function, negative 5, I want to plug in negative 1/3, and I want to plug in 2 into the original, and I want to see which one gives me the biggest and the smallest value. So this will be negative 20 e to the negative 15. This one's going to be negative 4/3 e to the negative 1, because 1/3 times 3 is obviously just 1, and it's negative. And then 2 is going to be 4 times 2, which is 8, e to the 24. 3 times 2, 24, 6. 3 times 2 is definitely 6. So the max is very evident. The max, there's only one that's positive. So the max of this function is 8e to the 6, and it occurs at x equal to 6 on the interval -5 to 2. Now for these two, we kind of have to figure out which one is bigger, or which one is basically, or which one is smaller, because we want the min. They're both negative, so obviously one of those is going to be the min. So I put these in the calculator, and this one gives me something that's super, super close to 0. It's negative 0.00006. There's more zeros in between. There's a ton of zeros. And this one's about negative 0.49. So obviously the min is going to be negative 4/3 e to the -1 at x equal negative 1/3 on our interval -5 to 2. So just remember, for these problems, and even the word problems that deal with these, like optimization, we want to make sure that we are finding our interval, checking the endpoints, checking the critical values, and whichever is biggest and smallest is going to be our min-max on that closed interval. So we just did a bunch of optimization problems, but I figured it was probably a good idea to at least put one optimization problem on here. So it says Sharon bought 30 feet of fencing to make a rectangular dog cage that will go against the house, thus does not need any fencing. What dimensions maximize this area? So this is actually a really easy one. So if we have a house and we're trying to put fencing to make a rectangular dog cage, that's fine. Then obviously our variables are x and y for length and width. So the function I'm trying to maximize is x equal x times y. Now the question is, if I'm going to use x as my variable or y as my variable, but I don't want both. So somehow I have to eliminate those by one of the constraints. Now the constraints in this problem I think is pretty straightforward. It's the 30 feet of fencing. There's only 30 feet of fencing to go around this to maximize my area. So my 30 feet of fencing has to equal the 2 x's and the 1 y. So why this is beneficial is I can just subtract the 2x, get y equal 30 minus 2x, and if I substitute it in, I'm going to get x times 30 minus 2x, or area equals 30x minus 2x squared. So now the big thing about this is we have to make sure that when we're doing this that we are picking a closed interval to deal with. It can't go on forever. So the smallest x could be, because obviously we're dealing with x, because that's the variable we chose. The smallest x could be a 0. Can't really be 0, but it can be approaching 0. And the biggest x can be is 15. Because there's two sides that are both x, so I can't make them 30, because then that would be a minimum of a total of 60 feet of fencing. So if I find a prime, that's going to be 30 minus 4x. So setting that equal to 0, I will find my critical value. So that's going to be 4x equal 30. So x equal 30 divided by 4, which is 7.5. So in my area function, and you can consider this area based on x, I'm going to check area of 0, which is 0, because 0 times anything is 0. Area of 15, but area of 15 is 0 too. Because if I put 15 here, 15 times 2 is 30, 30 minus 30 is 0. So my maximum has to be at this 7.5, whatever it is, because the other ones were all 0. So if I plug into the area formula, it'll give me what our value is. So that's going to be 30 times 7.5 minus 2 times 7.5 squared. So that's going to give me 112. 7.5, and this would be square feet. So the max area is 112.5 square feet, and it happens when the width is 7.5 feet. So again, a pretty straightforward one. I would certainly encourage you to look at the ones that we did on section 4.6. Some of those little more difficult ones deal with volume and area and things like that.